Hi, I'm Antonio Sala, and in this video we are continuing with the intuitive understanding on what the SVD decoupling and principal maneuvers are. In this video we will quickly review the previous example with one controlled variable and several manipulated ones with just different numbers, and we'll discuss the dual case in which we will have one manipulated variable but three controlled ones, which of course it's impossible. We cannot control three things with one, but SVD least squares, whatever will give us a clear understanding on what we can and cannot do. So let's go. The basic theory, if we recall, was that from this SVD decomposition we could identify principal maneuvers in input and output directions and principal gains in S. Pseudo-inverse and least squares problems were solved by swapping capital U and capital V and inverting the non-zero elements of S. And SVD decoupling amounted to implementing this kind of controller in which Q is the number of controlled principal maneuvers we decide, and K is a diagonal controller. In a first example, if we had a scaled gain matrix 1 minus 2, the SVD input direction was also 1 minus 2 but normalized to unit norm. Principal gain was the norm of 1 minus 2, square root of 5. And SVD decoupling ended up in this block diagram in which, let's say, a heater and a blower blowing cold air were operating in a load balancing arrangement in which load was assigned proportionally to the gain of each actuator. In a second example on the same line, example 3, in the materials, well, if we have 3 actuators, now all of them with positive gain, then the SVD of a row vector is just the norm, square root of 1 plus 2 squared plus 2 squared, 9, 3 square root, and 1, 2, 2 scale to unit norm gave this principal maneuver, and then we had 2 null space maneuvers, which were input movements that did not cause any observable effect on the output, and then SVD decoupling with these 3 actuators would imply just getting the error, passing through any PID, let's say, and sharing with these weights. To each of the 3 actuators, of course, this would be in incremental units and operating point to be added and whatever. So good. Let us now concentrate on the dual case in which plant, instead of being a row vector, it's a column vector. For instance, we'll have a plant with 3 controlled outputs and 1 manipulated input. And in order to better understand what we are doing, we can imagine this single heater that has a higher gain, degrees per kilowatt, let's say, in the center temperature transducer, and half the gain at the extreme ones. Then we will have an operating point, and our controller must decide the increments to achieve a given set point. So, suitably scaling things, my transfer function matrix may be 1 to 1. So, which is the SVD of that thing? Well, the singular value is the norm, square root of 6, and output directions are this one, which is the, let's say, column space in which 1 to 1 is preserved, but we just divide it by the norm to get a unit norm vector, because this is an orthogonal matrix. And then we have these 2 columns, which are the null space and they are the output increments that are not controllable, let's say, not feasible with this actuator. Let's say I cannot decrease the temperature at the extremes and increase the temperature in the middle. 1 to 1, either the three of them go up or the three of them go down, Then these null maneuvers cannot be achieved, or if some disturbance moves my sensor in these directions, then that disturbance cannot be counteracted. So our SVD decoupling or whatever must concentrate on this output direction that is feasible, that is controllable, realizable, depending on the book you read. And before delving with block diagrams and the like, if we see which is the pseudo-inverse, here we have it, and it again has the 1-to-1 proportion between the elements. So if we were thinking in open loop control with one actuator, we cannot achieve 3 arbitrary temperature increments, so we will try to fit the increments by least squares, and then using the pseudo-inverse, which can also be computed with the SVD stuff, okay, but the meaning of the pseudo-inverse means that my customer would provide a given increment of T1 desired, and then in order to compute the increment of U that fits these increments in the least square sense, which means that the increment of T1 achieved minus the increment of T1 desired squared plus the same with 2 and the same with 3. Well, the increment of U that minimizes this loss function, let's say, will be, this weighted average with 1-to-1 proportion, let's say, of the user provided increments. This is, let's say, an open loop interpretation. If I were, let's say, trying to, compute the optimal operating point. But then the closed loop interpretation of this is the SVD decoupling, which in this case there is no input directions because we have only one input maneuver to do, just increasing or decreasing resistor power. And then what SVD decoupling means in this particular case, in which this is just 1, that will be multiplying the error with this U transposed and using a single controller, Q is 1, to decide the single heating power we need. What is multiplying by this U transposed, the first column of U? YSVD U transposed times the sensor would be a weighted average of the temperature readings or of the errors, in which the error in the central sensor counts double. It's a weighted average proportional to the gain. If my input can move double a given sensor, then it will count double in the weighted average, and due to the underlying theory, that will be the optimal way to fit the set point temperatures in the least square sense. So if we now draw this idea in block diagram form, this is it. We compute the errors, we multiply them by these weighting factors, a complicated way to say 1-to-1, let's say, weighting factors. And then that weighted average will be the SVD error in the single principal maneuver we can do, and the PID will decide the increment USVD that, it's already in physical units because there is only one input direction, so adding the operating point will get the physical U to apply to my heater. So this would be the equivalent of the singular value decomposition inspired decoupling when I just have one actuator, one manipulated variable. Okay, you might say, come on, why complicating this? Why don't we just forget about SVD and do this? Controlling just the central temperature reading, because it's the one in which we have more control authority on it. And okay, that would be a sensible option, you know, and much easier to explain than this weighted average pseudo-inverse stuff. But okay, that depends on what my customer wants, in the sense that if my customer indeed doesn't mind that the extreme temperatures drift away from the operating point, as long as the center temperature is the correct one, then this would be okay. But if imagine that some liquid drops here and cools this extreme, then okay, this control structure would not respond to this cooling in this extreme, but this one would respond. But of course it would respond in the least square sense, so that it would hit a little bit more everything, so the left and right thermocouples would increase the temperature reading. Then, well, depends on your application. If you wish to control the three temperatures in the least square sense, which ends up being this weighted average sense, then you do this. If you don't wish these complications and you just want to keep things simple, then okay, you might decide to choose the highest gain sensor and control the center temperature. Okay, it's up to you. And the goal of this video is explaining the relationship of all these choices with the SVD, the composition of my gain matrix in this simple case. So we end the video here, and of course more complex cases will be discussed in subsequent videos. Thanks for watching.